So, in our subject selected topics in decision modeling, we are in our 35th lecture, that is genetic algorithm examples. So, in the last few lectures we have seen the genetic algorithm method and the process of the genetic algorithm. So, let us see some examples. We have also seen one example on the traveling salesman problem. Here are some more examples. Let us start with a simple one, that is, let us say we want to maximize x square plus 1 over a very small range, that is 0 to 31. So, when you want to do that, so we can use, let us say, binary code. So, binary code here we need a chromosome length of 5. Why 5? So, chromosome length of 5 is required. The reason is that number is between 0 to 31, that means a range of 32 is should be sufficient. That means 2 to the power 5 is 32. So, using that 2 to the power 5 equal to 32. So, we can have a chromosome length of 5. So, you see that if it is 1 1 1 1 1, it will be 31, and 0 0 0 0 0 will be 0. And let us take only a population size of 4 with a 1 point crossover and roulette wheel selection. So, first is we have to generate an initial population. So, let us say we have generated an initial population 0 1 1 0 1, this is the function, and 1 1 0 0 0 0 1 0 0 0 and 1 0 0 1 0. So, what exactly we have done? We have flipped some coins and got these zeros and ones. So, that is our initial population. So, initial population has got 4 chromosomes, that is 13, 24, 8 and 18. So, what we do with them? Let us see. So, first this is our initial population. So, we compute the fitness, that is the functional value in this case. Then we compute the probability, these Fi by sigma Fi. So, these are our fitness function values, this is the sum of all the fitness. So, if I divide, then this is the probability. So, with these probability we constitute the roulette wheel. So, you could see that the first one, the fitness is 170, the sum is 1137. So, 170 by 1137.15 is allocated to the string number 1. So, you see this is the string number 1. So, this is our string number 1. So, like this we allocate all the strings, and this is our expected counts. So, why these are expected counts? Because how many times out of, if I do it 4 times, suppose we want to select 4 parents, then what is the time we get these numbers. So, these are 0.6 to basically 4 times those numbers, but actually what we got is 1, 2, 0 and 1. How exactly we did this experiment? We again took some random number between 0 and 1. Suppose in the first time the random number comes out to be 0.3. So, 0.3 will actually, so 0 0 to 0.14 will select the first one, 0.14 to 0.64 will select second one. So, this particular number, say 0.3 or something, will choose the second string. So, like typical random number experiment, we got those actual counts. So, if you see the actual counts, we got 1 times the string 1, 2 times the string 2 and 1 time the string 3, string 4. So, that will constitute our the mating population. So, that is our mating population. So, let us see. So, this is how mating pool. So, look at the mating pool. The mating pool is that first one, second one is twice and the fourth one. Is it all right? So, arbitrarily we took some probability and we got the crossover points. So, 4 and 4 and here 2 and 2. So, after that if I do, let us say, crossover between these two and these two, then this is how the crossover has been obtained. So, how the crossover is obtained? So, look here, these 4 is equal to this 4 and this 0, that is 1, and this 4, that is this 4, and this 1, that is this. So, like this we have done. Now, here also these 2 and these 3. So, these 2 and these 3. So, these 2, these 2, these 3, these 3. So, that is how the crossover is made, right. Now, these are the offspring. So, look here, these offspring values are 12, 25, 26 and 16. So, this is going to be our next generation, and look at their fitness. Their fitness is 1705, that is the total fitness, and the average fitness is 426.06. So, the maximum is 677. So, you see earlier our maximum was 577. So, that was this value, and here our maximum is 677. So, you can see that neat solution has improved. The average solution has also improved, which was earlier 284.25, now it is 426.25. So, like these these things are going on, and we can also have some mutation. We took some random probabilities and see so many random numbers are required, because string 1 has 5 positions, same is 2, 3 and 4. So, assuming a mutation probability as 1 by 5, that is 0.2. So, we generate random numbers for all 20 genes, and we got in 2 cases the number is below 0.2. So, we do mutation out there. So, what is that mutation? 0 will be 1 and 1 will be 0. So, like this we can carry out mutation. So, you can see that what are the positions? The second string, third and fifth. So, this is the second string. So, the second string, third and the fifth, we had some mutation. So, what is that mutation? 0 becomes 1 and 1 becomes 0. Is it all right? So, that is how the offspring has become after mutation. So, after mutation, very interestingly, that the value has gone up. So, it has become 785. So, it is not that after mutation the value will always go up. In this particular case it has gone up, because mutation is mainly done to really improve population diversity. That is the main purpose. So, we have done that, and that is how you can see by the recombination operators of selection, crossover and mutation, the system moves from generation to generation. So, this is the essential idea of the process, the GA process. So, let us take another example, that is the second example. Suppose we have a supply chain, and in this supply chain we have some the demands from plant to the customers, is all right. So, we have the distances in kilometers from plant 1 to the various customer zones, and let us assume that the transportation cost would depend on those distance values. Is it all right? So, objective function is minimize the distance. So, that means plant 1 should supply to customer 1, 2, 3 or 4 or plant 2 will go to the other. The point is every customer zone must be having a supply. Is it all right? So, it is basically a kind of assignment problem. How do we do assignment so that the total cost is minimum? Now, look here, usually we try to solve such problems as maximization. So, our fitness function will not be same as objective function. So, that is the first thing to note. Alright. So, what we do? We could make some changes. So, let us say we make the fitness function as 100 minus d. Alright. So, minimize d is actually means maximize 100 minus d. Alright. So, that is how we can do. And selection by expected count, that is the roulette wheel, f by f average, and the crossover, you see this is the kind of crossover that we thought about, that suppose A, B, C, D and I, J, K, L are two parents, then child will be L, J, K, I and D, B, C, A. Basically, these kind of things are required because this is more like a permutation encoding, right. So, I have explained permutation encoding while discussing the traveling salesman problem. The permutation encoding will be something like this, that 1, 2, 3, 4. So, if another string is 2, 3, 4, then fourth number should be 1. Really, in assignment problem situations, it means 1, 2, 3, 4 means 1 to 1, 2 to 2, 3 to 3 and 4 to 4, and 2, 3, 4, 1 means 1 to 2, 2 to 3, 3 to 4 and 4 to 1. Alright. So, I hope you understood the crossover and mutation. So, A, B, C, D and I, J, K, L after crossover will become L, the last one should be first, first one should be last, the middle one remains as they are. So, here also A, B, C, D becomes D, B, C, A. Alright. Now, what happens that we choose some random numbers, let us say crossover probability is 0.8. So, we have some probabilities and we see that string 3 and 4 are selected for crossover in iteration 1, that is these two, because the probability is lower than 0.8. And here string 1 and 2, they will be selected for crossover because their random number is less than the crossover probability. So, this is how we make use of crossover probability to choose whether to go for crossover or not, right. So, with that, now let us see, these are the strings. So, this is the distance values and 100 minus d, those are the fitness functions. So, this was the original matrix. So, what we did for all the strings, we compute the fitness values, very simple. Simply look at the first one, just see what happens to the first one. This is the distance 20, then 9, then 23 and 7, just add them 1 to 1, 2 to 2, 3 to 3, 4 to 4. So, total distance will be 59, but had it been 1 to 2, so 25, then 4, the customer zones 4, 2 to 4, not that way, I think this is 14. So, that means 2 to 1, then 25, then your 17, the third one, that 3 should be on 17 and 30. 2 to 4, actually this 25 and this 17, not this one, right. So, 14, 25, 17 and 30. So, like this we compute those distances, and 100 minus d, that will give us the fitness function value. So, these are our fitness function values for those 4 strings, right. So, having obtained that, now let us see what we get. So, this is our strings, this is the objective function, these are the fitness function, then we get the f total and f average. So, if I divide by f total by f average, then we get, and multiply by 4, we get the expected counts. So, we got some expected counts for the initial population. So, in this case we made a simplified system, that depending on the expected count we find how many should be the number of strings. So, please understand that every genetic algorithm is different, and it is up to the designer to follow different procedures, that is different selection, crossover or mutation methods, right. So, there will be variations of this type. All right. So, then after that these are our mating pool. You see the string 2 and 3 are the same. This is nothing but the same 3 1 4 2 has got 2 copies. So, 2 copies 1 2 3 4 1 copy and 4 3 2 1 1 copy. So, this is our the mating pool, and through this mating pool we did crossover. So, 1 and 2 we choose for crossover, 3 and 4. So, 3 is 3 1 4 2 and 4 is 4 3 2 1. So, after crossover what they will become? See, this 4 3 2 1 becomes 1 3 2 4. Can you see that? This 1 has come here, 4 has gone there, and this string, this 2 has come here and this 3 has gone there. Is all right. So, that is how the parents and the childs are obtained. So, like this we have now some new strings, that is 1 2 3 4 3 1 4 2, these two remains as they are, they are replicated, they remained in the new population, and these 1 2 3 1 3 2 4 and 2 1 4 3 they join in the string, right. So, having obtained this, that is after crossover, then we see what is the new situation. So, these are our new strings, that is 1 2 3 4 3 1 4 2 1 3 2 4 and 2 1 4 3, and again we compute the d and 100 minus d by the procedure already shown. So, this is our new fitness function values. So, same thing is replicated once again, and look here, this time the F average is 35.75. Look what was in our earlier case, in the first generation it was 33.75. So, after crossover we found that, I mean, when the new generation is obtained, the new generation the having a higher average fitness, right. So, once again we compute those expected counts, basically 41 into by 143. So, that is if I divide 41 by F average, then I get those expected counts, and from the expected counts we can see some numbers, maybe we can obtain through random numbers also. So, that will be for our next crossover. In this case there is no mutation considered. All right. So, once again by same procedure we do the from the mating pool and crossover, and we get a new set of strings. So, all these new set of strings, once again we compute the d and 100 minus d, the fitness function values. So, this time if you look, then their new fitness values have become 35. So, this case what has happened, this fitness value have slightly reduced, right. So, it is not always that the procedure has to guarantee that average fitness value will increase, but overall the solution will be better. So, but then what is more interesting is that let us see what was the best possible string, that is also very important to see. So, you see the best fitness value here was 44 in the first generation in the initial population. Now, at the second also we had 44, right, but after the third generation also 44. So, we could not get a better string than fitness value 44 even after 3 iterations. At the third iteration maybe we could have got a better string in further operations, because it is a very simple problem. In a large problem we go for many generations, we have to have a computer installation of such problems, and we may get better solutions. All right. So, we saw at least one assignment problem and a functional value for how to solve by GA. Let us see some examples about the knapsack problem. So, we have already seen knapsack problem in dynamic programming, we have also seen in integer programming. So, it is known to us what is a knapsack problem. There are certain things, so like A, B, C, D, E, F, and they have different sizes and different values. So, total size is fixed, that is a 50, and that is to be filled so as to maximize the value, that is the usual knapsack problem. So, what is it that, see, assume that it is a binary knapsack, that is 0 or 1 should only be selected. So, if that is so, then we have an objective function maximize sigma I equal to 1 to n V I x I subject to S I x I less than equal to 50. So, what should be the fitness function? So, the maximize part is fine. Now, who will check this constraint every time we select and do crossover and mutation? See, the point is, if you leave it to the process, if you think that okay fine, I have got the string and I have this fitness and I will keep checking every time I do selection, crossover and mutation, it will be too cumbersome. So, a better method, that is called a penalty function approach, a penalty function approach. So, this approach essentially what it does, right, it actually adds these constraint in the objective function itself and converts the constraint problem to an unconstrained optimization problem. And however, it also means that it allows some infeasible solutions in the solution space, but their fitness value should be very, very low, is all right. So, how? Because so that they are so unfit, their fitness values are so low that their chances of getting selected in the next generation with crossover or mutation is very, very low, is all right. So, how exactly this is implemented? So, look here, this is an example. What we have done, we have created a new fitness function as sigma V I x I plus minimum of 0 and a penalty, say 1000, could be any other value, 50 minus S I x I. So, you see how it works. Assume that S I x I equal to 20, all right. So, S I x I equal to 20. So, what will be the value of 1000 into 50 minus S I x I? It will be 1000 into 50 minus 20. So, it will be 30,000. Can you see that? So, it will become 30,000, all right. Now, assume another example, suppose S I x I equal to 60. So, what this term 1000 into 50 minus S I x I will become 1000 into minus 10 to minus 10,000. So, just say I have given two examples. In the first example, if S I x I is 20, that is within the constraint was S I x I should be less than 50, isn't it? That was our constraint. So, in the first instance, that is sum over S I x I, yeah. So, in all these cases, it is actually the sum over is missed. So, this, please put that sum, right. So, this is the sum, that means the total value total I mean weight or something should be within 50. So, that is the sum. So, that is all. So, you see that when the value is 20, that means within 50, this evaluates to 30,000, and when it is above 50, that means not within 50, it evaluates to minus 10,000. In the first case, when it does not cross the limits, it evaluates to 0, because 0 and 30,000 minimum is 0. That means, this term will become nothing but VIXI, is it not, in this case, in the first case. In the second case, what will be this term? This term will be sigma VIXI minus 10,000. Can you see that? So, the fitness function is reduced by a huge margin, right. Those strings are going to have very, very low values. That means, they are actually infeasible, because they cross the weight, but they will be still considered, but with a very low fitness value. So, this is exactly how these problems are treated. Suppose we have these 2 chromosomes. So, what happens? We do single point crossover. So, you know already how it is. So, at the third point is the crossover point. So, 101 and 111 and 110 and your 100, right. So, those are 2 childs, and in 2 point crossover, if you do, then the middle portion will be interchanged, and the mutation will be simple bit inversion, is all right. So, that is how the crossover and mutation is done. Let us take another problem, which is not a 0-1 problem. So, there are things A, B, C, D, they are in different numbers, and the knapsack size is 150, the values and sizes are there. Here how do we go about? So, one thing you understand, that since it is not a 0-1 programming, the binary encoding is not going to work. So, what we have to do is we have to do real encoding, right. So, how real encoding is done? So, you see, you can have something like 4 digit 4853, which means 4 A's, 5 B's, 6 C's and 7 D's, all right. Fitness function will be as before, and single point crossover and single mutation may be used, right. So, what if the available are not 9, then use a suitable penalty approach, is it not. So, supposing if they are within 0 and 9, that is fine, but supposing the number is not 9, number is more than 9, then probably we have to use 2 digits each, right. We not necessarily penalty function all the time, we might have the real encoding of 2 bits each. So, the problem might have to be encoded in more than 1 bit for each item. Fine. So, this is how now in this lecture let us also see something very interesting, that is called tree encoding. See, this tree encoding is sometimes what happens, supposing we have an objective function and we really want a formula for a function, is all right. So, we want a formula for a function. So, basically we want a particular value to be maximum, some fitness function value should be maximum, but we want to know what is that formula, we want to actually discover the formula. So, something very interesting. So, we can do really tree encoding. So, tree encoding is used mainly for evolving programs or expressions. Every chromosome is a tree of some objects such as functions or commands in programming language. So, it could be a programming language also, something like do until step wall, something like this, but this can be read as plus x divided by 5y, is it all right. So, plus x divided by 5y. So, you see this is like a formula. So, if you add further trees, you can also really write a formula. So, this is the encoding. The encoding gives a formula, right. So, and this string then can be evaluated based on the given x and y values and see what kind of fitness function we are obtaining. So, sometimes like those empirical relationships we have to obtain. Suppose we know something depends on 3 values, but we really do not know what is the relationship. We have to discover that relationship, we only know their functional values. So, from the functional values we can discover the best possible empirical relationships by going for tree encoding, is all right. So, finding a function that would approximate given pair of values, input and output values are given, the task is to find a function that will give the best or the closest desired outputs for all inputs. Chromosomes are functions represented in a tree. And look how the crossover is done. So, if we have two parents, this is a crossover point for parent A and parent B. So, what happens that this portion gets replaced by this. So, we get a new offspring where it is earlier it was x into divide x and divided by y plus 3. Here it will become x divided by y square, is all right. So, that is the kind of interesting things that we can do with the tree encoding, right. So, this could be a little more complex, but just to mention that we also have tree encoding, right. So, I stop here and thank you very much.